Hello. In this video we're going to talk about the conditions for sampling distributions for proportions, right? And these are extraordinarily important. If conditions aren't met, we can't say that all of the theory we've been working on is anything we can use, right? So first let me address the sampling distribution technically is the ideal pattern that would emerge if we looked at all possible samples of the chosen sample size from the population. And it would be the distribution of expected samples. So what does that mean? Well, let's take a look. Suppose you were going to select 2 people from 9 people. And let's say we numbered the people from 1 to 9 so that we gave them each a way of identifying them. Then look at the combinations. We could pair 1 with 2, 1 with 3, 1 with 4, 1 with 5, 1 with 6, and so on. And if order didn't matter, then of course we wouldn't have to say 2 with 1, because we already have 1 with 2. But even so, look at all the possibilities of just selecting 2 people from 9. So imagine then, when we were looking at sampling 40 women who were from the population, 40 from a population of 30. Could you imagine selecting 40 from 300, what the possibilities would be? So this would give you an idea of how many samples really constitute a sampling distribution. It's thousands of samples, okay? Now, so what are these conditions? The conditions that must be met for all of this theory to work, and when I say all of this theory to work, what I mean is that we can actually use a normal model, right? That the samples cluster or pile up around the mean p and spread out by the standard deviation square root of p times 1 minus p over n. And of course, remember your book uses q for 1 minus p. So what are these conditions? All right, they're right here. Random selection, or you could say random sampling. Representative sample, or success failure. Both of these are synonymous in what they're trying to say. Independence and the 10% rule, right? So now, random sampling. Why do we need to show that? Well, essentially, random sampling ensures that people or objects are chosen without any bias or preference, right? Because if there's some preference to pick one person over another, all of a sudden, not everybody's going to get represented equally. So now what we need to do if we're going to select randomly is essentially eliminate the human component. When a human chooses, there's always bias. So if you notice when you read your text, random selection must involve some way of eliminating the human element, so that could be a computer choosing or some kind of a system. So now a human can be the agent, but they can't actually do the selection, right? So everybody has to have an equal chance of being selected. And then representative sample ensures that the sample size is large enough to represent the population. So to ensure this, what we found is that you really need to make sure that given a sample size n and population parameter p, your samples will have at least 10 people with the trait and at least 10 people who do not have the trait. Mathematically, this is written this way. Sample size times the rate at which the trait occurs in the population has to be at least 10, and sample size times the rate at which you do not have the trait has to be greater than 10. So let's take a little look at that. Now, let's take this example. Suppose we know 30% of people drink iced tea, right? And in a room of 60 randomly chosen people, how many people actually drink iced tea? Well, if we take 60 people and say, well, 30% of these 60 drink iced tea, then we should get 18 people drink iced tea. And that's more than 10. That's all we have to show. So then, how many don't drink iced tea? In these 60 people? Well, you could do 60 times, well, if 30% do drink the iced tea, then what, 70% don't. And that's where you're getting the 1 minus p, right? And so then you get, what, 42 don't drink iced tea. That's greater than or equal to 10. Or you could have just done what? 60 minus 18 would give you 42, right? You could have done it either way here. But essentially then you see that if the rate at which the trait is occurring is at 30%, then in general sample sizes of 60 yield at least 10. And they mean in general. I mean, sometimes, of course, with sampling variability, you're going to have, higher or lower than 18, but we're saying over the long haul, if this is the rate at which the trait occurs in the population, and this is my sample size, in general, I'll have about 18 people who have the trait and then 42 people who don't, right? Now, let's take a look at another example of this. Suppose, instead, that we know that only 1% of people lost at least 20 pounds in the last year. So in a room of 100 people, how many lost at least 20 pounds last year? Well, in this case, you'd say 100 people times 1% equals only one person lost at least 20 pounds last year. And that is definitely not greater than 10. So what just happened? I have more people, and yet, more people than 60, and yet I only had one person, and in the other case we had 18. So what just happened? Well, what happened is the rate at which the trait occurs in the sample is only 1%. It's very low. So of course, I have to go have a much bigger sample size to actually see that trait occurring in my samples at a level of at least 10. So what happens then is it may seem to you that 10 doesn't seem like a very large number to have to see in your samples, but look at what just happened, the balancing that happened, because if I wanted to see, well, how big would my sample size have to be at 1% so that I'd have at least 10, you'd say, what would my sample size have to be so that 1% of my sample would yield 10? Right? So then when you solve that, 10 divided by 0.01 would give you 1,000. So my sample size would have to be 1,000 so that I at least see 10 people with the trait. So this is where, in essence, there's this balancing act between the rate and therefore the sample size. And indeed, it does turn out that as long as you see 10 of each, 10 yeses and 10 nos, it's good. Your sample size will be representative. Okay? And the last two, we have independence. And what is that for? Well, it's to ensure reliable or truthful responses. All right? Now, how do we show that? Well, in one case, we could say one person's object's trait will not affect another person's object or trait. Okay? So what's an example of that? Well, if I say, say for example, I like to drink coffee. So whether one person likes to drink coffee or not, it really will not affect whether another one does. Okay, so, and it could be that somebody's, a friend could at least influence somebody to try a coffee, but in the long run, that person is either going to like or not like the coffee even after they tried it. You're not going to change that. So, a lot of times one trait will not affect another. And in that case, there is true independence so that you're getting a reliable response. What's another example? Well, let's say height. Okay. Well, obviously, one person's height will not affect another person's height. And so the idea is, when I go to measure someone's height, I'm going to get a reliable, truthful response. Okay. Now, why do we have this 10% rule that I put under independence? Well, the 10% rule, in the 10% rule, you have to show that your sample size is less than 10% of the total population. So what is going on there? that's when you suspect that the responses may not really be reliable. So let's give an example. Let's say you have a highway. Okay, here's a highway, and these are cars. A lot of cars just driving on this highway. It's an interstate highway. And you're going to see why I don't quit my day job to become an artist. Let's say there's a policeman there waiting to see if somebody's speeding. And let's say, indeed, someone is speeding. Okay, there's this really hot rod car, and this person's speeding, so they have to get pulled over, and the policeman is dealing with giving that person a ticket. Well, tell me, what happens with all these people that can see this person being pulled over by the policeman? You know, they might have been speeding, but what happens? They stop, right? They slow down. They want to look like they're just following the rules. They're not speeding, even though it's not like the policeman's going to change, going to stop processing this person and go after anybody here. It doesn't matter. These people all change their behavior. So all of a sudden, if you were trying to see, are these people speeding, you wouldn't get a reliable or truthful response. Why? Because this person's trait, the fact that they were speeding and got caught, is affecting all these people. So these people are not independent of what this person. But what happens is, let's say it takes this much time, these many people pass by, and finally the policeman has processed this person, and now what happens is nobody can see the policeman, he goes back there. So what happens is these people have no clue that, oh, there's a policeman there. So what are they doing? Speeding. So then what happens? Maybe this person gets caught and gets pulled over, right? They get pulled over, and when they do, what happens? All these people change their behavior. But that's okay, because when you think about how many people are driving on the interstate, does it really matter? The policeman's going to be able to have lots of fish in the sea. So that's the idea here. So as long as basically your population is more than 10 times your sample size, right, then it doesn't matter that these people are now, in a sense, contaminated. So the idea is, if I have a very large population, right, and yes, some people might influence another, one person can influence another person because they actually see what's going on. Doesn't matter. The idea is this: if this person is here and then these people are affected, it's okay. My population is so large relative to my sample size, I can say, well, I'm going to sample over here. These people don't know anything about what's going on there. So then these people are influenced. That's okay. I can go sample maybe over here. And so then maybe these people are influenced. But what has to happen then for this to work is that the population, right, is much greater than the sample size. How much greater? At least 10 times, right? And then that means you have room enough to just go everywhere and be able to sample here, sample there, and not have any of these overlap and therefore contaminate or affect each other, okay? Now, let me work a little bit with this. If the population has to be greater than or equal to at least 10 times the population, the population has to be greater than 10 times the sample size, then relatively speaking, let's go ahead and solve for n. That's usually how it's written in the statistics books. So what has to happen then is I'm going to divide by 10. Right? I'm going to start solving for n. So now these cancel out, and I have n is less than 1/10 of the population. But 1/10 is the same thing as 10% of the population. All right. So usually rewritten, they'll say n is less than 10% of the population. Okay. So that's usually how you'll see it, and that's why they call it the 10% rule. All right. Now, let me just mention this. When you looked at these 4 conditions, books vary as to which ones they really put a lot of importance on. Pretty much all books will say, yes, you have to have random sampling, and yes, you have to meet this success failure where you have 10 yeses and 10 nos. It's here that they vary a little bit. Do we have to show independence and 10% rule? Do we have to show a 4, all 3? Some of this stuff varies. I like to show it this way because I like to put that independence and then the 10% rule, in essence, has to do with ensuring that you're getting truthful responses. So please look at the comments. I made this video so that it applies to pretty much all stats books. Some books treat it a little bit differently, so please read the comments that I attach with this so that you'll know, oh, for our specific book, what does our author tend to lean toward? All right? Thank you so much for listening.